Dynamics unit. Today's lesson, I'm going to break it into 4 videos, one representing each example that I have, and it's just examples of stuff we did in grade 11 physics. Okay, so this first example, you should have it in front of you, of course, and me and Restall are pushing we don't have an echo anymore, but we had an echo, and we're pushing it out of the snowbank, and there's his applied force, and there's mine, and we applied just enough to get the echo moving with a constant velocity. Okay, so sort of 6 things the question's asking us for. The first one is the free body diagram. So let's remember what that is. A free body diagram is, we call it a force diagram, and it's always just a circle, and you draw arrows coming out of the circle in the direction of all the forces acting on this object. So in this case, I'm saying F always represents force, and, his force, R for Restall, so he's applying 2,500, I'm applying a little bit more, 2,800. N, you may not remember, but it's called the normal force, and we'll talk a little bit more about that another time. Then we have our kinetic, and it's kinetic friction, because holding the car back, and it's kinetic because we're moving. So you might remember that if you're moving or sliding, then it's called Fk, and if you're just starting to get it to move, that's when you use what's called static friction, or Fs. Okay, and Fg is gravity. Just some notes on the FBD. Forces are always F. There's where I tell you what the forces are. And I don't use a ruler, I'm not that precise, but in general, the size of the arrow should represent the size of the force. Okay? Since this thing's not moving up or down, my car isn't, these two should be about an equal size. It's not perfect, but it's the idea that my force is a little bit bigger than his force. And one thing maybe it's not totally clear, but this Fk, because I'm constant velocity, should be the same as those. But anyways, that's the free body diagram, and that's part 1. Part 2 asks us to find what's the gravity force on my echo. Well, you might remember that's always mass times g, where g in the kinematics unit, motion, is 9.8 meters per second squared, and it's what we call the gravitational field constant. So it can be using what we call an equivalent unit. G is also 9.8 newtons per kilogram. So this means every kilogram of mass experiences a downward force of 9.8 newtons when at or near the surface of the Earth. So if you hold a coffee, or it'd be a heavy coffee, but a kilogram in your hand, what you're feeling is 9.8 newtons downward. We'll talk a lot more about gravitational field constants another time. The simple answer, of course, is that to find the Fg, you just multiply the mass of the car, 850 times 9.8. Okay? Part 3 is asking us for normal force, and normal force is always, well, I have a few things here written about normal, which is, of course, why I had to make different videos for each example. I don't want them too long. But what is the normal force? What it really is, it's the reason we don't fall through a surface, or in this case, the surface of the Earth. Why you don't fall through a wall when you're leaning on it. It's not really a force. Well, it is a force, but it's not a real thing. What it is just that our electrons repel the electrons in the ground. And so it's really an electric force, but we call it normal. The things to remember is always perpendicular to the surface. Saying it's pressure isn't quite right, but it is a way to think of it. The more pressure there is between surfaces, the more the normal force. Okay? Like I say, I'm kind of lying to you when I say that, because it's not pressure, but it's when you think of pressure, the more normal. Less pressure, less normal. Oh yeah, this is where I said it's actually caused by the repulsion. There's sort of 2 things that actually are happening now. The repulsion between the electrons in our shoes and the electrons in the ground. The other thing is that, you always think of fan blade, things appear solid because all the particles in them are moving so fast, right? Like if you have a fan and it's spinning, it looks like a solid. You wouldn't put your hand, even though the blades of a fan don't take up all the space, you'd never, if the thing is moving, you'd never put your hand through, you'd never be able to, right? It's kind of the same thing. So part number 4 asks us to find the net force. Just a little thing, different terminology. I always called F net in grade 11. I always just go by whatever book I'm using as a reference, and the book that you have as a reference in this course uses this little thing. It's called a sigma. If you took data management, you've seen it before. So it's, and it is the sum of all the forces is what it means. So net force, that's how I say it now, net is mass times acceleration. That was from grade 11, Newton's second law. Because we have constant velocity, our acceleration is 0, so net force is 0. So that's easy. Part 5, it asks us to find the friction force. So net force is the forward minus the backward. And this is actually what it is. Net force is the sum of all the forces. So if you define forward as positive, then backward is negative, and that's why it works. But either way, the forward force is me and him, Fs and Fr, and the backward force is friction. Okay, so the net force being 0, we'll solve for friction, 5,300. Okay, and of course, just I'm going to scroll up here, just by looking at it, sorry. You look at the picture. The idea is that because there's no net force, these two have to equal that. That's the easiest way of thinking of it. Last but not least is looking for the coefficient of friction. So coefficient of friction, it's a measure of stickiness between the surfaces. It's that number between 0 and 1 that has no units. Remember mu? Okay. A high number means it's sticky. So in the way you find it, here's the formula for it. It's friction force divided by normal force. So we know those things already. And it ends up being 0.64, which I know is a good answer. I'll put a check mark on that. Good work, because it's between 0 and 1. Okay? Perhaps you want to use the same number of decimal points as the question. I just want to make a point here that when you're dealing with a number less than 1, it's probably 2 decimal places is good. You usually use, because this question uses 0 decimal places, but it wouldn't make sense to call them UK1. So we're going to use, just from a communication point of view, if with coefficients of friction, use 2 decimal places. Okay. Just a little aside here, the difference between kinetic and static. Friction, kinetic is when you have something sliding. Static is that, I said it earlier, if you're just getting something going. Okay. You can pause this to write this down. I think all these details are pretty easy. Static friction is greater than kinetic. Coefficients of static are greater than kinetic. So if you're looking at, you know when to use static if the question says to just start. That's sort of your trigger. Okay, so that's this example. It was probably the longest one, don't worry. And I'll do the other 3 as separate videos.